Welcome back, class. This is CSC 143. We're using Building Java Programs, Chapter 13, Searching and Sorting. I'm going to do things a little bit differently today. I am, again, using the slides of my dear friend of over 30 years, Amelia Gahn. Thank you. And I'm going to skip around in the chapter. Normally, the chapter actually covers searching and sorting first, and then covers the orders of algorithms, but I find that that's actually kind of backwards. So we're going to skip to covering the order of algorithms first, and then come back to searching and sorting. I've skipped ahead to chapter 13.2, Program Complexity. And complexity is a measure of the computing resources, generally time, but sometimes you can worry about disk space or memory. But in this course, we're going to be looking at the time that it takes to do things. And one way of figuring out how long stuff takes is simply to time it. But if you could actually try this yourself. You can try writing loops of 100,000, a million. You have to get to some really big numbers before a modern computer you can actually start seeing the time differences. So empirical, just measuring how long things take, actually isn't very useful, and very few people do it. I'll tell you more about some exceptions on that. Instead, what we like to use when we are designing programs is algorithm analysis. Before we even ever start coding anything, we consider what is the best algorithm by analyzing certain things. Now, ironically, most of your code, 90% of your code, we completely ignore in algorithm analysis. So it lists here a bunch of different things that do not involve looping, and we simply ignore it because it's fixed, which means that it's always going to take a constant amount of time, and that's not something we're really concerned about. And again, you might think, if we're worried about how long something takes, don't we worry about, if you've got 10,000 lines of straightforward non-looping code? In practicality, yes, that is something that needs to be considered, but but you really don't have any control over that. What you do have control of is algorithms where it comes to looping. There is also a note here saying, and this is interesting, that Java initializes array elements to 0, whereas in other languages like C and C++, when you declare an array, it doesn't take any time at all. It's constant amount of time. In Java, it's actually very expensive. There are other cases like this. For example, if you're concatenating strings one character at a time, each time you concatenate a string, it has to throw away the string and build a whole new string and add a character onto the end. And I'll tell you, we'll hopefully revisit that, and I'll explain why that is so bad. So we're going to analyze algorithms instead of looking at empirical data for how long things take to run. So the real core of algorithmic analysis and order analysis is looking at your loops. Okay, so loops are the really big thing that take a lot of time. So the runtime of a loop, it depends on how many items you're looping through. We're just going to say if you call the runtime of loop 1 m, so that would be like for int I equals 1, I is less than m, I plus plus. Okay, so if it takes m cycles to run loop 1 and n cycles to run a second loop that follows the first loop that is not nested, then you simply add them, m plus n. You can roughly say that's how much time something is. The big thing is when you nest loops. When you nest loops, you have an outer loop and you have an inner loop. And anytime you nest loops, you actually have to multiply the amount of time that it takes. And we could take a look at another example of this in a minute. But you have to multiply the amount of time because for every item in the outer loop, you have to go through every item in the inner loop. And so when you have a nested loop of length m and length n, it's no longer m plus n, it's now m times n. So it's a lot bigger. And in general, if you've got an inner and an outer loop both going over the same number of items, n, then we say that it's n squared. And that's a really expensive operation that we try to avoid. So we categorize algorithms by what are called complexity classes. And so there are various different complexity classes. We're going to go and take a look at them in just a second. It's determined by what's the biggest influencer, and generally that's the number of nested loops that you're doing. So n cubed, for example, would be a really bad algorithm. We almost never see an algorithm that's n cubed. You really want to avoid that. Whenever you have items that get added together because they're sequentially done, it doesn't matter whatever is the smaller item. So in this case, 4n, that doesn't matter compared to n cubed, sorry, and nor does 2 matter here. What matters is simply the n cubed. So we call this an order n cubed algorithm. So here's a list of the different types of complexity classes. These are increasing from the fastest algorithms to the slowest algorithms. So constant time, logarithmic, linear. This term here, log linear, it's technically correct, but nobody ever says that. They just say n log n. Don't say log linear. People will look at you strange. Quadratic is n squared. Cubic, pretty much we rarely see these kinds of algorithms, but the big one we're really concerned about is exponential. So let's take a look at some examples, and I'll try to explain where I've seen these in real life. And I'll also say that here's an industry minute. So I used to interview a lot of people for Microsoft, and we would always have a problem question. It's like a puzzle. And we would always try to have a puzzle that had multiple different solutions. And depending on how smart the candidate is, they could come up with a really, really slow algorithm or a really, really fast algorithm. So before I ever got started with coding, I would ask candidates to describe what their algorithm is going to be and to ask them what order is the algorithm. So you really need to know this stuff. I don't know whether they still do that these days, but I think it's still absolutely relevant, so I would be surprised if they don't. So these are really important things. So constant time algorithm means that you don't have any loops. So it can't involve anything where you're having to look down an array or look down the length of a string or anything like that. It's simply like, for example, multiplying a couple of numbers. And you might say, well, doesn't it matter how big the numbers are? Not really. It's a constant time factor for a simple mathematical formula. What matters is if you had 10,000 of those multiplications, okay, in a loop, that would matter. But for basic stuff that doesn't involve loops, it's going to be constant time. Logarithmic time, let's skip over logarithmic. Linear is the next most important. This is a really common one. Whenever you're looking down an array or a string, you have to look at all the elements where we would say there are n elements. Then we call that order n or linear. That's the most common type of algorithm, and it's rare to get any better than linear algorithms because you usually do have to look through everything. So that's the most common one. You know, if you were to do a count, a sum, a min, a max, a string length, any of those are all linear algorithms. So let's go back to logarithmic. So sometimes you can do better than having to look through every item in a list. So binary search, which we're going to learn in a little bit, is a case where you don't have to look through every item in the list. If you can somehow cut that list down to size and in half, and then cut it in half again, and cut it in half again, you end up taking log base 2. That's another key here, is that we don't list the base 2, but it's log base 2 of n. So if there are 8 items, the log base 2 of 8 is 3. So you could get it in 3 cycles. And we'll go over an example here. But so sometimes, if the items are sorted, you can do a logarithmic algorithm. Again, I never call it log linear. N log n algorithms, these are the most common kinds of sorting algorithms where you have to look over n elements. There's no way you're going to avoid looking at all elements because you have to see where each one belongs. But if you can figure out where it goes in log n time, then this is a really good sorting algorithm. The best sorting algorithms we have, the best ones known to man, are n log n algorithms. Okay, n squared is not a good sorting algorithm. So selection sort, there are lots of different sorts where you have to look through every item in the list, and then you have to look through every item in the list to find where it goes. So this is kind of the default. And again, when I would ask students interview questions, they would typically come up with, the simplest answer is to come up with an n squared algorithm. It's going to involve looking through a list in nested form, okay? And that's not the best way to do things usually. You ideally want to do an n log n algorithm. This cubed is not a real common. You rarely see things that are going to be cubic. The matrices is a good example if you have 3-dimensional matrices or something. So it's pretty rare. Now exponential is unfortunately common, and it's unfortunately common because in binary, we rely on exponential algorithms to protect our data. All of the security algorithms that you know of that protect your data rely on the exponential problem. And basically, think about binary. Okay, if you have 2 bits of binary, you can only store 4 bits of information. You have a third bit, now you can store 8 bits of information. If you get a fourth bit, now you can store 16 bits of information, 16 different values. So each time you add on a bit, it makes the program much more complex. It's not. We call it exponential, and that's why we use, say, for example, RSA 256 encryption. Or there's certain hashing that is like a hash 256. What that means is that we use 256 bits, which means there are 2 to the 256 combinations that you have to search through in order to find the right answer. And that makes it very difficult for anybody to break that kind of security. So exponential algorithms, we don't rarely commonly see them, but we use them all the time for security. All right, so what I want to do now is actually show you some examples in Eclipse of different types of algorithms. All right, here I've got a simple for loop. It's got just a single loop. It's ranging from 1 to the value m, which in this case is 100. And so when we run it, as you might expect, there's going to be 100 steps involved. So that's what we call linear. Okay, so it's linear. It's proportional to however many items we have to look through. Now the second one that I discussed was log base 2 of n. So what we can do, we need to search this loop faster than looking through all m elements. Well, if it was sorted, we could cut the list in half each time, and that's called binary search. We'll explain that algorithm more later. But let's just show you what happens if I'm able to cut this loop in half each time. So I'm going to multiply this by 2 instead of adding 1. Multiplying it by 2 means that we have half the list to look through. I'll set a breakpoint, debugging breakpoint right here. And let's step into it, and you can see, so counter right now is at 1. The next time counter becomes 2, then counter 4, 8, 16, 32, 64, and then 128, it stops. So that took 7 steps. So we went from 100 to 7 steps, and 7 is roughly log base 2 of 100. So 2 to the 7 would be 128. So, so we saved a lot of time by cutting the list in half each time. So that's a great advantage. Let me go back now to linear, and we're going to add an inner loop to this. So I've modified this with a nested inner loop. So we've got m items on the outside. So there's going to be 1 to m here, and for each of those 1, it has to go from 1 to n here. So as I mentioned, you actually have to multiply m times n. So if I run this now, it takes 10,000 steps. So that's a lot more than the 100 steps we were looking at before. I also want to show you, so this is what happens when you nest them. What happens if you don't nest them? You have sequential loops. Let me show you that. Here I've moved that inner loop to be a sequential loop. Terrible name, but it'll preserve the work. So now when I run it, it only takes 200 steps. So it's a huge difference from whether you nest a loop or you make it sequential. And I see this problem, not a lot, but sometimes students will not really realize what it means to nest a loop in terms of efficiency. You want to avoid nesting a loop if you can avoid it. A lot of times you can't, but it's always good to avoid nesting loops. And the next level of algorithm we talked about would be n log n. So what does that look like? That's where you have an outer loop of n elements, and then the inner loop, let me restore that inner loop. Okay, I've restored the inner loop, and then we're going to do that same trick where I'm going to skip half, divide the list in half every time. So now we're going to do an outer loop and an inner loop. Let's go ahead and take a look at the debugger, at least just briefly. So when we get here, the outer and inner are both 1, but now watch the inner variable. So inner becomes 2, 4, 8, 16. So it's only going to take 7 steps before we go out to the outer variable being 2. And so each inner loop, instead of taking 100 steps, takes only 7 steps. So let me continue on and delete that breakpoint. Continue on, finish. So it finishes the entire loop in 100 times 7, n log n steps. So n log n steps is a lot faster than doing it in n squared steps. So I'm not going to show you the code for exponential algorithms, but in essence, an exponential algorithm makes you add on another nested loop each time you increase the complexity. And again, that's really for binary things. So I could enumerate through all binary combinations for 2 digits by 2 binary digits by having these outer and inner loops. To do 3 digits, I've got to write a third nested loop. To do 4 digits, I've got to do a fourth nested loop. So the complexity really grows quickly. But that's an exponential algorithm. At this point, you should take a look at Practice It and do self-check 13.9, 10, 11, 12. These are all big O problems, order notation, and they want you to come up with the notation. You can put it in this type of format, n squared, n log n, etc. And you have to analyze the code. What you're looking for is how many loops. In this case, it's a while loop. Doesn't matter whether it's a for loop, a while loop, or whatever. And you have to look for how many elements it's looking over. So n is what this loop is really controlling. This loop. J is starting at 1. And in this case, you see that j is being doubled each time. So hopefully you remember from what we just talked about what happens when you double the amount of the loop counter, which cuts the loop in half each time, basically. So if you can do that, you get a very nice bump in speed. So think about what that is going to be based on what we just talked about. Here's another one here. So now you've got a one loop here, and it looks like it's based on n. It goes from 1 to n. You can ignore all these mathematical, that doesn't matter. Here you've just got an if statement, so you can, and it's got a simple mathematical, so you can ignore all of that. Really what you're looking at is just the one loop here. So think about that in terms of what we've seen so far for one loop. Big O3, now we've got several loops. So we've got 1, 2, 3 different loops, but you have to pay attention to where the loops are and what their limits are. So here you've got a sequential. These two are followed by this one. So this one is sequential, and it's going to be, it's actually going from 1 to 100. So it's actually a fixed length loop. And I didn't make that specifically clear, but if the loop is a fixed length, then we can actually ignore it, because it's a constant amount. But even if this were n, we would still ignore it because it's not going to be nearly as big as this nested loop up here using n. So here we've got a nested loop, and this nested loop here goes from 1 to n times 2. And that factor of times 2, you can ignore it. Anything that's a constant factor, just ignore it. So we've got an outer loop that has to go over n elements. And then an inner loop, again, it goes from 1 to n. So we have an inner loop going over n elements. So that means you're going to need to multiply when you come up with your order notation. So this turns out to be the biggest factor right here because we've got nested loops. You could ignore that. You could ignore the constants. Finally, big O4. Again, we've got 3 different for loops, but let's take a look at what's going on here. Now it's going from 1 to n. Again, the times 2 didn't matter anyway, so that's not changing anything. Now we've got j going from 1 up to I. Now what is I? I is based on this loop out here that goes from 1 to n. So you might think that that makes a big difference, but actually it doesn't, because I is still proportional to n. Even though it starts out small, unless I were to somehow be cut in half each time, it's not going to matter. So you still have 2 nested loops that are proportional to n. Here you notice that it's adding 2 each time, but adding 2 isn't good enough. You'd have to like double j in order for it to affect the order of the algorithm. And again, a sequential a loop isn't going to overtake a nested loop. And here these are all constant values anyways. You're going from -50 to -1, so that's not going to make any difference. So you should be able to do those big O algorithm problems fairly straightforward. So I skipped ahead in the book to section 13.2, program complexity, but now that you understand program complexity a little bit better, now I want to talk about searching and sorting. And even if you don't understand the complexity better yet, by the time we're done looking at all of this searching and sorting, I hope you will. So searching and sorting is extremely common. You can't really do anything of substantial value without having searching and sorting in it. When the data is stored in an unsorted structure, you're going to have to look through every single item in order to find it. Index of is an example of a linear search. Remember we talked about order linear algorithms? That's because you have to look through every single item. So if there are m items in a list, it's going to be order m to look through every list in order to find index of. So that's kind of the straightforward, most common case. But as I mentioned, if your data is stored in sorted order, you can do better. You can actually go to a log n algorithm, such as binary search. And I want to point out that binary search is not just for programming. Binary search is actually useful in real life. One of my first really popular videos was how to fix icicle lights that you hang up at Christmas, because icicle lights can have hundreds of lights in them, and you don't want to sit around trying to test every single light. Well, I figured out that if you could split the set of lights in half each time, you could go from looking at 200 elements down to less than 10 elements. So that is a real life example of where binary search works. So both the Java arrays and list classes have binary search methods built in. You don't actually have to write it. You can just call it. And what it does is it tries to break the list in half each time and then figure out which half is it in. But it only works if it's in sorted order. Let's take a look at an example here. So we've got almost all the numbers from 0 through 9. If I was to search for 2 in this list, I would first break the list in half and start here at 5. And I would see, nope, this isn't the right element, but I know that 2 is going to be on this half of the list. So this is where I'm going to search. And then I would again break this list in half and check to see which half is it going to be in. And I would see that it's going to be in this upper half. And then I would repeat again, then I would find it's here. If I was to search for 1, you could break the list in half. You see that it's going to be in this half, and then you get lucky and you find that it's actually the next breakpoint. Searching for 9, you're going to have to go down through this. Searching for 3, in this case you don't actually find it, but you'll eventually get to the point where you realize you can't find it because it's not. You keep on narrowing down this list, and you realize when you get to here that you can't find it. And we're going to look through, I think, the exact algorithm for this later. So the way you use binary search is you can either use it on the arrays class. So that is a helper class for arrays. Obviously, when you use arrays, you don't need to use classes generally, but if you want to do binary search, you have to use the arrays class. And there's a binary search method, and you can give it a number to look for. If you're using any of the Java collections class that we've been covering in the last few chapters, you can use a binary search that is built into the collections helper class. In this case, we're using an array list, but there is no ArrayList.binary search. Instead, you have to use this helper class, collections, and call its binary search method with the item. So binary search only works on sorted data. I think in this case, the numbers are not sorted properly. Let's see, where's the error here? Well, it goes to 92 and then 29. So it's not going to be able to find necessarily the item here. It's not guaranteed. It might not. The algorithm's going to get fouled up. So that's just the important point, that you need to have it sorted. There's a small discussion in the book about why don't they just, the algorithm automatically sort it for you. Well, the problem is that it takes more time to sort a list than it does to look up the list in binary search. And generally you don't want to modify the input either. So for those reasons, it counts on you to guarantee that the list is sorted. So that's an excellent segue into sorting. So sorting is a very important function, and it's a complicated function. There are whole classes that can teach you about sorting. One of the most famous people in computer programming at least in the history, is Donald Knuth, who teaches at Stanford. Maybe not sure if he still teaches there, but there are 4 volumes produced by Knuth that go over algorithms, and searching and sorting makes up a huge percentage of those algorithms. So we don't expect you to be able to produce these on the fly. So instead, the Java collections automatically provides both the binary searching and the sorting methods for you. It's great. So there are, you can either use arrays.sort for if you're going to deal with an array. And again, so if you're dealing with an array, you're not typically using classes, but you can use this arrays.sort method to sort your basic arrays. Or if you have one of the Java collections, you can use the collections.sort method. That gives some details as to the particular algorithm. I wouldn't worry too much about that. What's important to note, though, is that they are n-log n algorithms, so they're fast algorithms. So we're going to have a little bit of a digression here into using comparators. I call it a digression because it's not super common that you need to use this. If you're using a Java collections with a known data type that already has a compare to, so it relies on comparable. You have to implement the .compare to. If it already has a comparable interface, you're just going to use the Java collection sort or the arrays.sort. You don't need to worry about comparators. But what if you actually want to sort in a different order than the quote normal order? Or what happens if you, and also if you implement your own class. So for example, in my class, I have my students implement their own classes that implement compare to. If you do that, then again, you don't have to use comparators. You would just call collections.sort. And since you've implemented compare to, it'll just work. But if you're trying to use a predefined class in a non-standard order, only then do you need to worry about comparators. So this is less important, but I still need to cover it. So comparators let you, as I said, use do comparisons in a non-standard way. This isn't exactly the best example here, because if you were doing points, well, I guess if you were using the Java points class, then sure, you're going to have to use a comparator. But if you're creating your own point class or something like that, then you would just write .compare to, and that would be a better solution. So there is a predefined comparator. I'm going to talk to you a minute about how you create a comparator, but there is a predefined comparator, and I hate the naming of this. The comparator is called CaseInsensitive Order in uppercase. The reason I hate it is because in most languages, anything that looks like this is it's a static. It's a predefined value, and this is not a predefined value. This is actually a method. It's a comparator. It's actually a class, I think. So it's kind of strange to me, but that's just the way it is in Java. So if you use string.CaseInsensitive Order, that will give you a different ordering. It's case insensitive, as you might imagine. So they find it's a convenient form. I wish that it didn't look like a static value, but instead somehow conveyed that it was a comparator. That would, at least if it had the name comparator in it, that would be nice. So you can use this string.CaseInsensitive Order. I believe we'll also cover that you can do reverse orders as well. So here's how you create your own comparator. And again, you don't typically have to do this, but what you have to do is create your own class. In this case, it's length comparator, and there's only one thing that it needs to implement. You have to declare that it implements comparator. So you have to implement this method compare, and I find it annoying that why isn't it compare to? I don't know, but you do have to implement this thing called compare. And then once you've created that, now what you have to do is you have to pass in new length comparator, whatever the name of the class is. So I also find that bizarre. You're creating a new class as a parameter just so you can use this method over here. I think that's rather weird. I think it has to do with some language restrictions in Java. Anyways, if you do that, then it will sort your item with this new ordering for the sorting. All right, so in all of these examples, these are all things that you can use. It provides comparator here, but you don't need the comparator if you're going to use the default order. So we talked about arrays binary search and collections binary search. Arrays.sort and collections.sort. There's also a collections min and max, a collections reverse order. So yeah, this is what I was mentioning. There is a way to get the reverse order. This provides a comparator. So this looks more like what I would expect for a comparator because you see that it's a function. But still, it should say reverse order comparator. Anyways, so in my class, I don't want you using collections.min or collections.max because most of the time I actually want to see you writing that code, but it is possible. It is there for you to use. And then we talked about the string insensitive order. And there are also some precautions around the case-insensitive order. If you're doing Unicode in different languages, that case-insensitive order may not work. Now we're going to get into the nitty-gritty of how you actually implement searching and sorting. And another industry minute, it is totally fair game for people to expect you to be able to, without hesitation, write the code for binary search or for some sorting algorithm. It's kind of like, if you know anything about Boy Scouts, it would be like tying a bowline knot for a Boy Scout. You know, you just expect that if they're a Boy Scout, they'd be able to do that. And it's the same for programmers with some sort of searching and sorting. So it's an important thing to be able to do. So we're going to start out really simple. So for searching, the basics sequential search is you're just going to look through a list here. So they're going to go down the length of this list and check whether each item is there. And as we talked about in the order analysis section, that's going to be an order n algorithm because it's for n elements, it's going to take roughly order n time. But you can do better. If it's sorted, you can do a binary search. And I'm going to skip ahead to showing you exactly what that code looks like. We already did an example here, but now we're going to get into the nitty-gritty. So you are going to split this list in half, but exactly half is difficult. You're going to actually use integer division. So in this case, we've got elements 0 through 9. There's 10 elements. So you split it in the middle would be 5, but in terms of indices, you go 0, 1, 2, 3, 4. So this is on the low side of this half of the list. And just the way that the algorithm works, we're always going to pick the low side. You could probably do it with the high side, but it's just going to be done with the low side. So we start looking at element 12, and the value that we are looking for is a target of 5. So we know that 5 is less than 12, so we know we need to look on this half of the list. Now you could start by looking at this item all the way from -3 to 12 again, but really there's no point in looking at 12 because you already looked at it. So we're actually going to go one less than 12. So we're gonna reduce the maximum here. The maximum is going to be whatever that middle value was minus 1. So now we're going to look from the 0th element to the 3 elements. So there's from the first 4 elements here. We're going to repeat, and we're going to split this list of 4 elements in half, and again we're going to end up on the low side. So we're in details, we're going to add 0 and 3 and then divide that with integer division by 2. That ends up with index 1. So then we're going to check out this item here, value 2, and we're comparing it to a value of 5. And so we know that 5 must be on the high side of this. So we know that we're going to need to not look at this element, but we're going to move the minimum to be that midpoint plus 1. So now we're just looking at these two elements here, 0 and 1. You add those together, 1 you divide it by 2, and that becomes integer 0. So then we're going to check that value there, and we're going to find if the number at that midpoint is the target, then we return that. So in this case, we were lucky, we found it. That algorithm is actually, it seems simpler than it is when you actually have to write the algorithm because of trying to track the minimum and the maximum and the midpoint and getting that adjusted at each step. It's actually a fairly tricky bit of code. It's actually easier, believe it or not, to write this recursively. So we can eliminate all of that having to worry about what's the maximum, what's the minimum, and whatnot. Well, you don't have to, you can't entirely eliminate it, but I think this code here looks a lot cleaner than the other code. You still have you adding the maximum and minimum divided by 2 and checking whether that is that's the value. That's your base case here. But otherwise, you simply got two other recursive cases. Either it's going to be on the number is less than the target, so you want to look at the right side, so you're going to take the midpoint plus 1 till the end, or it's going to be on the left side, so you're going to go from the minimum to the midpoint minus 1. Now let's take a look at that code again compared to this code. No, you decide what's going to be easier, but once you try to actually write the code, you might find that it's not quite as easy as you thought. And also, I wanted to point out that you always need to check to see that the minimum is less than the maximum. In this case, we actually found the value, but in cases where you don't find the value, what's going to happen is that you're going to increment that minimum or decrement the maximum, and they're actually going to overlap. And that's when you know that the number doesn't exist. So it's here in both this iterative algorithm, and it's here in this recursive algorithm. This is just a caution that if you're going to be writing that algorithm on objects, then you need to use equals and compare to. So a sorting algorithm, the basic sorting algorithm is just called selection sort, and it's a really simple, intuitive algorithm. Let me just show you what it's doing. So it's really simple. If you were to sort a list, what would you do? You would probably find the first thing, that the lowest number here, 20, and you're just going to put it at the beginning. So here we swap 20 and 47, and then you figure out what's the next biggest thing. Oh, 26, so that's already there. What's the next biggest thing? Oh, it's 47, so we swap 47 and 77, and then we've got what's the next biggest thing? Oh, 64. So at each point, you're just going in and swapping whatever is the smallest number. And in terms of order analysis, you've got, what do we got here? We've got one loop here that goes length, that's basically n, from 0 to n. And then we've got another loop in here, and it goes from I, so that's the first loop, to again n. And we already discussed in practice it's how if the start of the index, the starting index is based off of this outer loop, but it's just like adding 1, that's not good enough. It's still basically an order n there and an order n here. So you're actually going to end up with an n squared algorithm. So you can see how that works for a selection sort. And that's a real common but basic algorithm. It's too slow. So we need to get to a faster algorithm. So one that the book covers is merge sort, and there are many different types of sorting algorithms, but this is a simple one that's easy to teach. The basic idea is you're going to split the items into two pieces, left and a right half, and you're going to sort each half and then merge the two. And this is the framework of the code for merge sort. You're going to create a left and a right. You're going to sort those two halves and then merge them back together. And here's the code for merge. And then the trick is that when you want to sort those two halves, all you have to do is just recursively call merge sort on the left half and the right half. And again, this is where recursion really makes things easy, because you don't have to write a lot of code to be moving pointers or indices around. You can just figure out your left half, you figure out your right half, you call merge sort on those two, and it comes back. And we're taking advantage of recursion's ability to kind of handle a bunch of variables for us. So what is the order of this algorithm? So because we're able to split the length of the list in half at each level, we still have to look through every single item at least once. So that's an order n. And then internally, we can actually split the list in half. So we're actually ending up with an order n log n algorithm, but because it's written recursively, it's really hard to see that here. So unfortunately, order analysis on recursion, it's a bit challenging. I wouldn't expect you to be able to do that very easily, but this is a very easy algorithm for you to see and for you to write. And the book actually has some excellent examples of merge sort. You should take a look at that. Here's a random example I found on the internet of how merge sort works, very similar to how the book is showing it. So you take this array, you split it in half, and then you merge each half. In this case, it's actually ending up on the high side. It's taking the first 4 and then the last 3. And then you take this and you do the same thing. You split it in half, so then we got half and half. And we haven't really done any work yet. We're just splitting it in half. Here you split it in half, split it in half. Now comes the work. So when you're merging it, that's where the work really is, because then it's figuring out, okay, this one goes before this one, so we're swapping the orders here. And then this one have to get swapped. So we're really doing work there. And then we're coming in and we're saying, okay, well, the 3 has to come first, then the 27, then the 38, and then the 43. And then finally, we're coming down this last merge here where we take the 3 from here and the 9 from there, the 10, the 27 from here, the 38, the 43, and then the 82. So the merge is really doing the work. It's the splitting is just kind of setting us up for success. But that is an example of how merge sort works, and you should definitely be able to do this, a drawing of this, to figure out where the splits are for the merge sort and how it merges at each step. That concludes the lecture portion, and now we're going to take a look at some more practice hits that you can do in Practice It. So here it's asking you to, if you perform a binary search on an array of 1 million integers, what's the closest number of elements? So remember we've talked about binary search and how it's a log n algorithm. So you don't have to be a mathematician at this. If you look at all the options, figure out what is going to be the closest to log n. So remember it goes 2, 4, 8, 16, 32, 64, blah, blah, blah. So you're not going to have to, for example, examine 3/4 or 750,000 of the integers, right? Eventually, you're gonna get the number a lot sooner than that. So figure out which one is the closest. There's 2 problems that ask you to figure out the indices for a binary search example. So they want the indices that are examined here and then the value that's returned. So here's the indices 0 through 14, and then here's the values here. So I'll do the first round. So binary search is going to start with index 0 and 14. It's going to add the 2 and then divide by 2. It just so happens that works out for integer division. It's going to be index 7 exactly. So the first number there is going to be a 7. Then you have to figure out where is the value. We're looking for 42, and we compare it with the value 39. So we know that 42 has to be on the right side here, and we know that it's not at 7. So we don't bother looking at 7 anymore. We need to increment the minimum to be now 8. So we're going to be looking from 8 to 14. And you just want to repeat the exact same thing. You're going to do the add, you're going to do the divide, you're going to do the compare, blah, blah, blah. So you should be able to walk through the rest of that. This is a very good example, counter example, because in this case you're not going to find the value. -5 is not in this list area anywhere. So it starts out the same way. You're gonna take your minimum, your maximum. You're gonna add. You're gonna divide by 2. You're going to check to see where it is. But eventually you're gonna get down to somewhere around here where you're looking for it. Remember to keep on either incrementing if we know that it's going to be in the right half. Remember to increment the middle value, the middle index up. Or if we know it's in the left half, remember to decrement the maximum value down. And eventually, you're going to find that the minimum is greater than the maximum. And that's the point at which you know that it's not there. Okay? So that's the number you're going to return. You're going to return a -1, but they have a binary search algorithm shown in the chapter, and you need to use that algorithm to get the exact number correct. So I'm just going to review these items. I won't tell you which one is the right one, but it should be pretty obvious. So selection sort, what do we know about selection sort? That was the straightforward sorting algorithm where we had to go through each of the n elements and then look for each of the n elements again to see what's the smallest number in the n elements, and then we move on to the second element, and we would find where's the smallest of the second elements. So that's a fairly complex algorithm. Merge sort, remember, that's the one where we split the list in half each time. So when you split the list in half each time, that gives you a logarithmic type performance. Merge sort runs faster because it's recursive. Recursive doesn't run any faster than iterative. Oftentimes recursive will be a little bit slower, but that's not not the case for recursive versus iterative. Selection sort, that's the one where we go through and we talked about that. So unfortunately, a selection sort doesn't, it actually, in real life, it would run faster if the items are sorted, but it's still not going to affect the order of the algorithm because you cannot guarantee that, for example, you're cutting the list in half each time. You can't guarantee that. And then comparing ints to other types. So that's a constant order operation. So it really wouldn't play into a complexity analysis. The last problem we're going to look at in chapter 13 is this merge sort tracing. And if you think back to the diagram that I showed you earlier, you just want to follow that. The only trick is just trying to make sure that you get the merge sort algorithm correctly for the indices. In particular, that example I showed you, when there were an odd number of items, it grouped the left half to the extra element with the left half, and in the book's algorithm it should be grouping it into the right half, I believe. You shouldn't run into that problem here because everything's even, but in other cases you will find it, so you'll have to group the extra element into the right half. So that concludes the exercises for chapter 13. If you've liked this video, please like and subscribe, and stay tuned for chapter 14.